okay, this is it. It's going to be a graph of a, or graphs of rational functions. That's it. So we give you the instruction of how we're going to do it. Okay, in order to sketch, okay, the graph of this function, a rational function f of x equal to numerators on the top, denominator on the bottom. This is what you are going to do for us. You have to do all these details when you want to graph it, okay? So, you know, if you want to just graph it, you can use a graphing calculator, your cell phone. I would like to be able to analyze it. So the first thing to do, you have to find the domain of the function. Okay, so you are going to find the domain of the function. Find the domain. You know how to find the domain. You let the denominator equal to 0 and exclude the zeros of the denominator. The second part is you try to simplify. Okay, simplify if it is possible. If it's possible. Okay, you write, you know, we write the function into reduce form. So then you are going to find the vertical asymptote. Okay, so you are going to find all vertical. You know the instruction for finding it. We already talked about it. So find all vertical and horizontal asymptotes. The techniques is going to be the one that we talked about it before. We are not going to give you anything with the slant asymptote, okay? So it's going to be vertical and horizontal one. And so we are going to check any intercepts, okay? Find x, okay, and y intercepts. I'm going to tell you how I'm going to do it. Okay, so this is going to be the case. So we check the intercepts. That is going to be the case. Number 5. Number 5 sometimes is going to be useful. Okay, check for any symmetric property. Okay, most of them can be done without, you know, checking this one. But check for any symmetry or symmetric property of the graph. Symmetric respect to the origin, you know, symmetric respect to the origin, respect to the x-axis or the y-axis. Okay, so this is the one that I have extra besides the one that you have in your book. We would like you to, okay, we are going to preview the graph if you like. I'm going to explain what does it mean, okay? Preview the graph. Okay, I'm going to tell you what does it mean in case you want to calculus. This way we do it. And number 7 is you are going to use all those information. Use all those information, the one that we have, information to get the graph, okay? To sketch the graph. The graph of the function. It's basically, there are a couple of more, but you are not going to have those type of things. There's something we call it intersection of the asymptote, horizontal asymptote, and the graph. So your graph are not going to be such complicated one. If you do the pre-calculus, they give you those type of graph as well. Okay, so this is the procedure that you have to take in order to get the graph of the function for us. Okay, any question? We are interested in 2 types of graphs. Okay, I'll give you one from each, and we give you 2 in your next quiz, 2 on the test, and usually 1 on the final. Okay, so let's get the first one. Any question? So I go to the next page so I have enough space to talk about it. This is just, so if you keep it in order, it's a nice and easy graph. So there you are, type 1. 2 examples. This is it. Sketch the graph. Sketch the graph of each function, each rational function. First one is the most popular one, and most of the time this is the only one that you're going to use in future. Okay, and this is it. The top is going to be, let's say, having x plus 1. The bottom one would be x minus 2. That's a type 1. Degree of the top and the bottom, both of them are going to be 1. We get a nice graph in this case. There is nothing complicated about this one, but you have to give us all the details that I'm going to talk about it. Okay, are you ready? Domain first. You know that. Denominator is 0 at 2. So the domain would be everything except 2. Solution. Okay, domain. You know that you have to exclude the, okay, exclude the negative 2 from the number line. So your domain would be negative infinity up to the 2 union with 2 and positive infinity. That's domain, step 1. Okay, so that was the domain. Any question? It's like, the asymptote first steps. Next, you check to see if you can simplify it. There is no chance. So I call it reduced form. So you are going to have y equal to x plus 1 over x minus 2. That's a reduced form. Step 2, okay? Next, asymptote. You know that the vertical asymptote is easy. You let the denominator equal to the 0, x minus 2 equal to the 0, so that gives you x equal to 2. That is your vertical asymptote. Remember, it's a line, so you have to write it down as x equal to 2, not just VA equal to 2. Doesn't make sense. That's a vertical asymptote. Okay, we go with the horizontal one. You know that you use it by shrinking. It's going to be x plus 1, x minus 2. You shrink the top into the xx equal to 1. So y equal to 1 is going to be your horizontal asymptote. So that's horizontal asymptote. Any question? Intercepts. You replace x by 0, you get the y. You replace y by 0, we get the x. Okay, x equal to the 0. X equal to the 0. Y would be equal to 0 plus 1, 0 minus 2. So that gives you negative half. Okay, that is y-intercepts. You let y equal to the 0 to get the x. Y equal to the 0, the fraction, x plus 1 over x minus 2 would be 0. We already talked about it. A fraction is 0 if the top is 0, because the 0 is like 0 over 1. So you let the top to be equal to the 0. So that gives x plus 1 equal to the 0. So x is equal to negative 1. That's it. So this is all you need. Domain, reduced form, vertical asymptote, denominator equal to 0, get the result. Horizontal asymptote, you shrink it. If they are going to be, x, you know that's going to be ratio. If the degree of the bottom is higher, the result would be 0. And you are not going to have the slant asymptote. Okay, intercepts, replace x by 0, get the y. y by 0, you let fraction to be equal to the 0. The top to be 0 to get the result. Okay, now preview. So let's see what we have so far. X, Y. You see, you start by, you get the x equal to 2. It's asymptote, so y is infinity. Y equal to 1. It's asymptote, x infinity. You put x equal to the 0, you get negative half. And y equal to the 0, we get the negative 1. It's all the information that you have. Any question? These are optional, okay, but would be useful. Now, you see the preview is going to be this one. It's the way we do it in future in calculus. It's going to be good for you. You just put the numbers for the x. It's going to be from negative infinity to positive infinity. The numbers that you have, and negative 1, 0, 2. Negative 1, 0, and 2 is the number that you have for the x. Okay? On the second row, the number that you have for the y. Y, the function. When x is infinity, y is 1. It doesn't matter what, positive or negative infinity. When x is a negative 1, y is 0. Okay, when x is 0, y is a negative half. At 2, y is infinity. It's asymptote, vertical asymptote. Vertical asymptote, okay? So this is how you're going to plan it. Any question? So this means if you graph it, it's going to be 2 portions. You see 1, 2. 1, 2. Now that gives you an idea of what type of graph are going to have. You look at the nature of the y. You see the y, the value of the function. From 1 we get to the 0. From 1 to the 0, it's a decrease, so the function going down. From 0 to the negative 1/2, it's done. So this means it's going down. Where? To the bottom of the asymptote. You see, that is going to be the case. So this portion start from the, you see this is asymptote, horizontal asymptote to the left of the horizontal asymptote. It starts from the left, you see, and it's going down. So that's going to be one form of your graph, if you like, from this part. Then you're coming here, the other side. The other side, you don't have anything to discuss. So you better pick help. Pick a number between 2 and positive infinity. Okay? If you pick a number, you may pick 3 here. Okay, you go back and you drop it into the function. You see x equal to 3 in the function. Remember, this is your function. X plus 1 over x minus 2. So x is 3, 3 plus 1, and the 3 minus 2. So that gives you 4 over 1, which is 4. So this is 4 here. Okay, at 4 to the 1, it's going down. So this means you're coming down from here. What is this? This is the asymptote, the top of the vertical asymptote, and you go down, down, down to the other part of the asymptote. So it's going to be the sub, see, this is going to be the other part. You see, that gives you very nice, this is exactly the graph. And that, you know, if you need anything, you just get this anything here. Then you are ready to graph it. You see, you bring all this information here and you get your graph. You draw your asymptote. You see x equal to 2, x equal to 2. This is x equal to 2. You see the other asymptote is y equal to 1, y equal to 1, y equal to 1. Okay, so we get the asymptote by dot line. This is x equal to 2. This is x equal to 2, and this is going to be, okay, y equal to 1. Exactly what you did over here, you bring it here. So you start from here, you see, you start from here. You're going down, -1 and 0. This is going to be -1. Okay, -1 and 0. Then you go to the 0 and -1/2. 0 and -1/2, 0 and -1/2, and you go down. You see, this is what you are going to do. Okay, exactly the way, the way we did it over here, we preview it. Okay, you start with to the left of the y equal to the 1, you go to the -1, 0, 0 and -1, and going down to the vertical, your vertical asymptote. Any question? Here, you start from the top. The top. You're going down. Where are you going? 3 and 4. 3 and 4, that was 2. 3, 4. This is going to be 3 and 4. And then you go down, you see. This is going to be the graph of the first part. And you're done. You see, very nice preview to get this graph done. And some people, they don't write, these ideas here, and they try to graph it, but you should be precise to get these numbers. If you're going to be in calculus, there's going to be one more row. So it's nice to preview it for us, okay? Preview your graph, okay? Then you just translate this one to here, and then you are done. It's going to be either down, 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 or it's going to be, up, up, up when we get these parts. So it may be something here or something here, okay, in the second and the third quadrant, or it's going to be just the first and the third one. This is all you get for these type 1. Any question? So nice, just follow the instruction. All of them would give you the points, okay? If you just graph it without all this instruction, you get 3 out of 10, okay? Because all these, you need to explain it, the domain, okay, the simplification, vertical asymptote, horizontal asymptote, x-intercept, y-intercept. The table is optional. This is optional, but we need, just give us the graph, the nice graph, which is going to be consistent with your information. We accept it right away. Any question? That's type 1. The type 1 is the one that, it's just a nice, this is it. You get everything, we need. There was nothing complicated about it. Okay, ready for type 2? What is the type 2? I'm going to write it down, then you will find out when I'm doing it, okay? So we want to graph this function. Let's see what is special about this one. F of x equal to, okay, f of x equal to what? It's going to be equal to the x plus, okay, this is going to be x plus 3, and this is going to be x squared minus 9. Okay, we want to graph this function for you. Okay, are you ready? Go for it. Exactly the steps that we talk about it. Follow the steps. Solution. Domain. Okay, this is it. You want to find the domain. And you have to factor it because that's x squared minus 9. So f of x is going to be equal to, we got the x plus 3 on the top, x plus 3 times x minus 3 down the bottom. Remember, don't simplify it now. Get the domain. The number is going to be 0 at two places, at the positive 3 and the negative 3. So we have to take out two numbers out. Okay, this is it. Most of the people, they miss it right at the beginning because they simplify it. It's going to be a negative 3 and a positive 3. Okay, so what's going to be your domain? The domain would be 1, 2, 3. Okay, three portions. So your domain would be negative infinity, negative 3, of course, parenthesis, a union with, it's a negative 3 and a positive 3, and the union with 3 and positive infinity. So that would be your domain. Any question? So we're done with the first step, the domain. The second one that you shouldn't miss is simplification, reduce form. You simplify it if you can. Of course we can simplify it, and that would be so useful for you. Okay, so how about a reduced form? Yes, this is it. We call it y. It's x plus 3, and you have the x plus 3 times x minus 3. You see, common factor out, so that give easy graph, to easy function to graph. So your function from now on is going to be what? It's 1 over x minus 3. Okay, you must simplify it, but you have to simplify it in a proper place or the proper time. The time is after the domain. Okay, any question? Now we go for the rest. Vertical asymptote, easy. Remember, you work with this function from now on. Vertical asymptote, you let the numerator equal to the 0. The number is x minus 3. X minus 3 equal to the 0, so x would be 3. So that's your vertical asymptote. Horizontal one, easy because the degree of the bottom one is higher. So if you shrink it, you know that there is the x down the denominator, that fits the problem. When the degree of the bottom one is higher, this always goes to 0. You know that. Goes to 0 as x goes to positive infinity. Because we get a pizza on the top, infinity on the bottom. So we divide pizza into infinity many parts. The result is going to be 0. So your horizontal asymptote is 0. Okay, question? So the vertical asymptote, you let the numerator equal to 0, that give you x equal to 3. And horizontal asymptote, you shrink it, or you can use the fact from your book that if the degree of the bottom is higher, so y equal to 0 is vertical asymptote. Okay. Next, of course, intercepts. Okay, intercepts. You let x equal to 0. But remember here, x equal to 0, y would be what? 1 over 0 minus 3, which is a negative 1/3. Okay, so y would be negative 1/3. This is going to be your y-intercepts. You let y equal to 0. Y equal to 0 means a fraction equal to 0. But that's a fraction. A fraction is 0 if the top is 0. Top is never 0. So this means there is no, okay, you have no x-intercepts. So the graph of the function won't intersect the x-axis, okay? No x-intercept, just for your information, no x-int. Okay? So this is all the information that you're going to have. And you can preview it if you like. Okay, so I put this information that I have. Then I preview it. It's going to be x and the y. So what I have is, I have the vertical asymptote is 3. So y is infinity. Horizontal asymptote is 0. So x is infinity. Okay, and I put x equal to 0. I got the negative 1/3. And I didn't get anything for the other one, and it's clear because that's infinity. Okay, so I can preview it now with this information that I have. So this is going to be my preview. This is an x, negative infinity, and the positive infinity. The number that I have for the x is just 0 and 3. 0 and 3. So what do you have for the y? So what do you have for the y? When x is infinity, the y is 0. So it's going to be 0, 0. When x is 0, the y is a negative 1/3. And when x is 3, you have the asymptote. So your graph is going to be these two portions to get these numbers. Okay, any question? Get the direction from 0 to negative 1/3 is done. So you go down where? Down the bottom of this asymptote. So now you know that your first version is going to be this one. Okay, how about this one? There is no number here, so you need help again. So you need help, like 4 that we did before. So get the 4, drop it to your function. You drop it into y equal to the 1 over x cubed, okay? x3. So this is it. If you put the x equal to the 4 into the y is 1 over 4 minus 3, which is going to be equal to 1. So it's going down again. So it's going down again, so your function is going to be of this format again. So it's very similar, or it is the same as the one that we did for the other one. Any question? So let's graph it here. That's it. Asymptote. You have x equal to 3. X equal to 3. 1, 2, 3. So that should give us the vertical asymptote. That's a vertical asymptote. Then the other one is just y equal to the 0. Y equal to the 0 is just the x-axis. So that would be your asymptote. Any question? So y equal to the 0, horizontal line, is going to be just the x-axis. And x equal to 3 is just a vertical line. Okay, now you know the idea. You know that you are here. So what do you have? You have a 0 and negative 1/3. 0 and negative 1/3. And you know that you have to start from here, going to, 0, going to this point, and then you go down. Go down of your asymptote. Okay, on the other side, you get 4 and 1. You know that you have to start from top. You start from the top and you go to the what? You go to the 4 and 1. This is 4, and this is going to be 1. So your graph starts from here and it's just going down. Okay, it's going down. That should give you your your graph to get this number. But you're not done. Okay, you have to do something about. Remember, there was a common factor that you eliminated. Look at this one. You see, domain of the function is everything except 3 and negative 3. The one you eliminated was x plus 3. So you have to identify x equal to negative 3. You see, this is 1, 2, negative 3 here. Then you see, this is going to be the point that you're going to get for the negative 3 on the function. But you don't have it, you remove it. So you have to make a hole here. You see? Anytime you remove that common factor, because when you remove it, you don't have it. You cannot have x equal to negative 3. So you suppose you do have a -3, and then you make a point. So this point you have to exclude it. So the graph is like the part one, but there is a hole inside the graph. Anytime there is a hole, this means there was a common factor, and you eliminate that common factor, and that is why you have to have the hole here. Okay, so most of the people, they miss it. They miss this part, but you have to identify it, because domain of the function, remember, domain of the function is all real numbers except 3 and -3. X equal to 3 is happened to come with the asymptote, but not the other one. So you have to make a note. Just make sure that you are going to exclude it from your graph. So that is the point about the second type. So the second type, if you get a chance to simplify it, your graph, when you graph it, there is going to be a hole in your graph, okay? And you identify it because you don't have that number, okay? So just make sure that you identify that part for us and show that you did take care of that part. Otherwise, it's very easy graph. It's like the first part, because you remove it, it's going to be more or less like the first part. Okay.
Quick question.
Yes.
So when we simplify it in step 2, would we be able to just use that instead of never mind, finding the intercept?
You mean you're using the original one?
Yeah, would that still?
No. It give you the same answer.
Yeah, but will it always give us the same answer?
Yes. Yeah. They give you the same answer over here. Okay, but you better not use it.
Okay.
Okay. Yeah, I mean, they should give you the same answer, because that factor would be out. You see,
Hmm.
that factor would be out. But as soon as you simplify, you better stay with the simplified form. You see,
All right.
through the end to get these numbers. Okay, because you know what? If you put y equal to the 0 in the original one, look at this one. If you put the y equal to the 0 in the original one, then what are you going to get? You get that the top is equal to the 0. If you let the top equal to the 0, what are you going to get?
-3.
-3. But -3 is not the domain of the function.
Yeah.
Okay, so if you have this one in your mind that you are going to check it, yes, but you better play it safe and go into the reduced form, so you don't have to worry about it. Okay,
All
so this is it, and the hole. The graph would have a hole if you have a common factor, and you have to identify that hole for us. Okay, so that is a type 2. Ready for type 3? The type 3 is more exciting. The type 3 is that you see this one, it was x squared, but because of that common factor, you remove it. So there's going to be something that you cannot remove it, and this x squared stays the same. So you are going to have two vertical asymptote, okay? So that's the one we call it case 3, okay? And a quite interesting one. And this is all the possibilities. So the type 2. So we call it number 3. And this is it, something easy. Are all the same, this type of procedure. They give you something like, how about 3x? And this is going to be x squared minus 1. Okay, so this is the one we call it type 3. The type 3 is that there is x squared down here, and it's not going to be removed. So you are going to get two vertical asymptotes. They are very popular, many applications. Okay, so let's check. Are you ready? Solution. Step 1, the domain. We have to simplify it. You have to factory domain. So f of x would be, we get the 3x on the top. Okay, so that gives you x minus 1 times x plus 1. So you have two numbers to exclude. I mean, you don't have to write the graph, but this is the way I do it. If you can give us the domain right away, we accept it. Okay, so you have three portions, 1, 2, 3. So the domain would be negative infinity to the -1, union with, okay, the -1 and 1, and the union with 1 and positive infinity, okay? So that's going to be the domain. Reduce form, you cannot reduce it, but we write it down to say that I did check it. Okay, reduced form, simplified form, it's the same. So we're going to y equal to the 3x, either version with the factor or otherwise, okay? So this is it. We cannot simplify it. Now we are ready to go for the vertical asymptote. So we did check vertical asymptote, denominator equal to 0, denominator is x squared minus 1, or x minus 1 times x plus 1, whichever you like. So you know that the result is going to be what? It's going to be x equal to the -1, one asymptote, and x equal to the +1, another one. So we're going to have two vertical asymptotes. Any question? We go for the horizontal one, then we have to shrink it. Denominator degree is higher, it's 0. You can claim the 0 right away, we accept it, or otherwise I'm going to shrink it. So it would be shrinking to the 3x and the x squared. But one of the x's would simplify, we get 3x, and that's a pizza problem because the x make it denominator infinity, so this would be 0 as x goes to infinity. So this means, y equal to 0. We can say y equal to 0, we accept it right away. Because when the degree of the bottom is higher, it is always going to be a leftover than the denominator. Okay, so we got the vertical asymptote and horizontal one. We need to check the intercepts. Okay, and that's easy for this case. So our intercepts, this is it. We did x equal to the 0. So y would be 0, 0 over -1, which is 0. Which is 0. So it's 0, 0. You don't have to check the other one. So this means this graph passing through the origin. To get these numbers, okay, that would be interesting because you see this horizontal asymptote, which is y equal to 0, and we get a 0, 0. This is the case that the graph of the function would pass through the asymptote, if you like, and that's fine. Okay, previously, sometimes the people, they say, oh, be careful, and the graph cannot intersect the asymptote. No, it can. That's the case that we have. Okay, now we can preview it if you like, and that would be very useful to do for this one especially, okay? So the information that we have collected are going to be, so what we have the x equal to the 1 and -1. So we get a positive -1, and these are the asymptote. You can write it down separately or together, it doesn't matter. Okay, and for the y, we get the 0, and that was the asymptote. And at the same time, we get the 0, 0 here. That's fine. So this means there is an intersection between the graph and the asymptote at the 0, 0, and that's fine. So if you preview it, you find out that you need more information to be able to graph it. Let's see. You see, this is going to be your preview. So what we have the x from -infinity to +infinity, and the numbers for the x are -1, okay, and we get the 0, and we get a +1. Okay, the number that you have for the y, when x is infinity, the y is 0. When x is a -1, it's asymptote. When is the 0? It's 0. Okay, and width of 1, it's asymptote. That's it. That's all you have. So you need more information to be able to do it. Otherwise, you cannot graph it. Because in each version, now you don't know what is the direction of your graph. Going up, going down. Okay, so we start from here and bring more numbers. Between negative infinity and negative 1, for example, you may bring the negative 2 here. Okay, so let's go to the function and to see what's going to be the result when you put x equal to the negative 2. So your y, the function would be, remember that was 3x. It's going to be 3 times the negative 2. And the bottom one would be negative 2 squared minus 1. So the top would be negative 6. And the bottom one is 4 minus 1. Okay, which is a negative 6 over 3. That gives you a negative 2 here. Okay, so we can add these numbers here. That would be useful if you like. It's a negative 2 and you have a negative 2. So that gives us a negative 2 here. So from 0 to negative 2 is going to be done. So this would be down of this negative asymptote, or the x equal to the negative 1. So that will tell you that, in this version, this is going to be this type of the graph. Okay, any question? Now, the difficulty is here. Okay, you have a negative 1, 0, and 0, 1. So you have to check one number between negative 1 and 0 and one number between 0 and 1 to see what is going to be the shape of your graph. So between negative 1 and 0, we may pick a negative 1 half. Okay, negative 1 half, negative 1 third, doesn't matter. So we go for it, x equal to the negative 1 half. If you don't like a fraction on the top is 3x. You may go with the, okay, may go negative 1 third. Okay, that's fine. Give you a chance to simplify it a little bit, but eventually you have to simplify everything. So it's going to be y equal to, okay, so that gives you 3 times a negative 1 half, and the bottom one would be negative 1 half squared minus 1. So the top would be negative 3 half. The bottom one is a quarter minus 1, okay, which is going to be negative 3 halves. And this is going to be what? Negative 3/4. Okay, a quarter minus half. And if you simplify it, you can simplify the negative 3 and negative 3, or just write it down. You know that it's going to be negative 3 half times the reciprocal, which is going to be 4 over negative 3. So these two would cancel out. Everything would be out. That give you 2. Okay, so in this case, we get the 2 here. Okay, from 2 to the 0, it's going to be done. So you start from the top of this asymptote and you go down to the 0 so far. Okay, any question? So what we can do, another number here between 0 and half. So if you pick the 1 half, it's kind of symmetric property. They get the 1 half, only the negative what would be different. So that gives you a negative 2. So this means you go down again. You see, you go down again and you go down again. So what is going to be the shape of your graph here? You see the shape of your graph, you start from the top, you see, you start from the top and you go to the 0 and you go down, down, down. So this is going to be the shape of your graph. Okay, any question? But you have to go down here. You see, between 1 and positive infinity. If you put the, so that gives you a positive 2 here. Okay, and for the x goes to positive infinity, that was 0. Okay, so this means it's going down again. So you start from the top and you just go down. to get this graph, if you like. Okay, as you can see, without preview, you won't be able to get a nice graph for this part over here. Okay, I didn't check it for you, I didn't emphasize, but look at this problem. We did it at the beginning of the course. Remember, 3x over x squared minus 1. This graph is symmetric with respect to the origin. So that's why you will see these numbers. You see, look at these. You get the negative 1 half half, you get 2 negative 2. So the graph is going to be kind of symmetric. You can use this symmetric property if you like, but it's not a big deal. You have enough information to graph it, to get these. It's always happened with this third type. Okay, it's not bad, but you need to get these numbers nicely. And now we are going to graph it now. Any question? So when is it?
Yes.
Yes.
How do you know that it
Yes.
goes down between the asymptote and 2?
Here,
No,
you
the next
see
well,
this
either
one.
one.
No, you see this last one. I just check. You see x equal to 2. You get y equal to 2.
Yeah, but
Okay, and this is 0.
asymptote.
You see, 2 to 0 it's going to be down here. So when I guess that, I get the 2 0. But here you see, what you did is we start from the top one, negative 1 half, that give you 2. Then 2, you get the 0. 2 0, it's done. So I check the next number. You see, I check the negative 1 half. That give me a negative 2. So from 0 to negative 2 is done.
Yeah. I'm talking about
Okay?
from the second asymptote to the 2. How do you know that it's down?
You mean this asymptote?
Yes.
You, you see, the nature of these parts going to be all the same. So if you pick somewhere that's going down or up, that give you down, down, down here. So what I did, I have this number. You see, look at this one. And then I have this part. So from 2 to the 0, 2 to the 0 is done. So then I realize that it's going to be down, down, down. So I start from the down here. Yes, you got it?
Yeah, I'm good.
Yeah, it's kind of symmetric. Then you will see it in the case. But you have one number to check. You see, I have a 2 and a 0. Between 2 and positive infinity is done. So for this part, this portion of the graph, it's decreasing. It's not going to be up and down here, you see. It's going to be just down, 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 or up, 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 and you really got it. But this may be different. It's all down, okay. Sometimes it's going to be the other way around. It's down, then it's up. Okay, there is a case that is going to be, that version. And now we are ready to graph it. We have all the possible information that we need. Okay, so what I do is I need more rooms, and I want you have this information, so I give you you see, this is what would happen exactly for graphing. It's a very nice case. If you are going to be in calculus, you have to give us 2 more charts. That takes something like 15 minutes on the test. That's why I usually avoid it in calculus, not in your case. You'll be able to do it. So we are going to get the asymptote. We have 2 vertical asymptote at 1 and negative 1. Okay, so this is it. This is 1 and this is a negative 1. So this is what we have. Okay. These are going to be a vertical asymptote. Okay, x equal to negative 1 is one of them, and this is x equal to the positive 1. Your horizontal asymptote is the x-axis, y equal to the 0. So this is, the other part. And you already got the preview. You know that you must be here. Okay, this is, you are here, then you are coming down through the origin down, and this is your graph. But you have the information. You see, you start from here, according to your graph. You see, you go to the -2 and -2, and then down the other asymptote. Okay, so I have a -2 and -2 already. So this is a -2, and this is going to be a -2. Okay, so I have the point, it's a -2 and the -2, and I know what's going to be my graph looks like. So I go down these asymptotes. So that's the first portion. Okay, any question? For the middle one, I know that I have to come from the top. Okay, I have to come to the top, going through the 0, 0. You see the information, you have quite a lot of information. At a -1/2 is equal to 2. Okay, -1/2, 2. So this is it. So remember that was 1. So this is a -1/2, -1/2 and the 2. Suppose this is going to be 2. So this is going to be 1 point. Then I come to the 0, 0. This is going to be 0, 0. Then at 1/2, it's a -2. So I go to this point and then I go down. So this is it. I come here. Okay. Then I go to this point and then down. You see, this is going to be the second portion. And the last portion, I did have the 2, 2. You see, this is going to be 2, the 2, 2. So what I have, I'm going down here, and then that give me the graph of the function. As you can see, this graph is symmetric respect to the origin to get these numbers. So it's always for these cases with the two vertical asymptote, this is going to be the case. If you get x squared minus 1, this is the 1. If you change it to the 1 minus x squared, it's coming to the 0 and just get back up here. Okay, that is going to be the shape of your graph. So this is the only case that I just wanted to say, really, something nice. And you got to be patient, get those numbers nicely, but you have to preview it, really. If you preview it, you can do it. But some people, they get the vertical asymptote, they start from here, and they get some numbers, okay? They get a couple of points to find out how they are going to end up. But that preview of the graph give you all this information that you need and nicely be able to, okay, to graph it, to graph a nice thing. The way you do it in calculus is, you see this, where this direction would be changed. This one, we call it curving down, curving up. We have a tool in calculus that we able to do it. But if you do calculus for business, they just stay with the polynomials, really. They don't graph it. But they like to know it. It depends on the book that you're going to use for calculus business, if you are measuring that discipline, or it depends on your instructor, whether they like it or they just want to skip through it. But you have all the information that you need, in case they say that you should have seen it in college algebra, and that's going to be the one we did. Okay, so that is sketching the graph of the rational function. 3 cases, and we give it 2 out of 3. Okay, and we practice it before your next quiz and before the test. Okay, I'm going to give you a short break, if you like, because then we are ready to get that famous function, really very nice one. We get to the next chapter, chapter 5, and that is going to be a very important part of your course, this chapter. It's quite a dense one, but you need all this information if you want to take the next course. So we covered everything on chapter 5. We try to do the exponential function if we can, some part tonight. Okay, that's 8:14, 10 minutes. We come back, we give you a nice introduction to the exponential function. Okay, see you in 10 minutes. Okay, so we are going to give you introduction to the exponential function. This is chapter 5. Okay, uh, number of the mathematical modeling in business. Okay, in science. If you want to talk about it or to apply it, you need this type of function. Okay, especially exponential function. So that's why we need to know it. Okay, so this is going to be 5.5.1. Okay, 5.1, and what is exponential function? Okay, exponential functions. Okay, just check to see this is going to be, yes, exponential functions. Okay, so what's going to be the idea of the exponential function? You see, we have a different type of functions. Depends where the variable is. That function would give its, a special name. If the variable x is down the denominator, the function, that's called rational function. If the variable x is inside the radical, we say it's a radical function. Now for the exponential function, the variable x is an exponent, okay, an exponent of a number. That's why we call it exponential functions. So first, we want to remind you that how are going to work with the exponent of a number, okay, and what are going to be the possibilities first, okay? So before getting to the definition, we just want to remind you the following, okay? So let's review something first, and then we go to the definition. You see, we already worked with the following exponents. So if I ask you, simplify, okay, simplify each so-called exponential, okay, exponential expressions. Okay, so you can do it. For example, if I ask you 2 to the, okay, let's say 2 to the fourth, we know that 2 to the fourth is going to be what? It's going to be 2 times 2 times 2 times 2, which is going to be equal to the 16. So we know how to operate with the, okay, if the exponent is going to be a positive integer, we know how to do it. Then if I ask you what is 25 to the half, means if the exponent is going to be a rational number, you can do it because you can say that 25 to the 1/2 is radical 25, so it's equal to the 5. So I can do the rational exponent, okay? If you make it a little bit more complicated, again, I can do it. So if we say, oh, what's going to be 8 to the 2/3? So we say, okay, 8 to the 2/3. We can write it down as 8 to the 1/3 first, then we square it. Okay, 8 to the 1/3 would be cube root of 8. Then we square it. Cube root of 8 would be 2, so 2 squared would be 4. So this is how we take care of, the exponent of the form of 1/2, 1/3, etc. Or we get a 2/3, 5/3, this type of powers, okay? So I can do the rational power. Then the other one is the negative power. So if I give you 5 to the negative 2, again, we can do it. Because the 5 to the negative 2, we write it down as 1 over 5 squared, and this is going to be 1 over 25. So we can do even the negative power, okay? So this is going to be the result. Or if I give you, the base are all greater than 1. If I give you a number which is going to be less than 1, like 1/2 to the third, again, you can do it. Because the one that is going to be what? 1/2 times 1/2 times 1/2, which is going to be 1/8. Okay, so we can do all of them. But if I give you this number 7, if I ask you what is 3 to the radical 2, okay, what's going to be your answer to this one? Any suggestion? Can you find 3 to the radical 2? see, we can do the positive integer. We can do the negative integer. We can do all sorts of fractions, okay, rational numbers. So we can do all of them. If we can do 3 to the radical 2, then we say we can use it for any real numbers. Remember, the real numbers are going to be rational numbers or just a radical function, if you like. Now, the situation with this 3 to the radical 2 is we cannot do it, okay? But we can estimate it because radical 2 is not a precise number, okay? So to answer to this one, we say, oh, this is it, radical 2. Radical 2 is approximately 1.4. Is approximately 1.4. So this means I should find 3 to the 1.4. Now I can use my calculator. We can use your calculator and get an estimate for 3 to the 1.4, which is going to be 4.65. So this is going to be an estimate for the 3 to the radical. If you use your calculator, you see, if you directly use your calculator, the calculator give you this one, 3 to the radical 2 is going to be approximately 4.7, depends how many decimals you would like to, okay, to have, you see. So it doesn't matter, we can do it. So we can do any powers if you like. Why we do this type of operation? Remember, when we use the variable x for the function, variable x is free, is a free agent. This means x can stand for any real numbers. So that will help us. That will help us that if I keep the 5 as the base, but I replace this one by x, that give me 5 to the x. So 5 to the x, I can define it as a exponential function with the domain of all real numbers, because I can use any real numbers over here. Okay, so that's a preview of what we are going to do. So we can introduce a function in which the variable is exponent of the numbers. And that variable can be any number you like. It can be positive integers, negative integers, rational number, or the fractional one. Okay? And the base can be greater than 1, 5, 8, 25, 2, or it can be less than 1, 1 half. Okay, it can be 1 half, 1 third, etc. So that is a motivation for us to introduce a new machine. That new machine is exponential function. So what is the definition of the exponential function? Okay, so I need a base. So suppose base, I go with a b. b is a positive number. Is a positive number with one condition. The condition is b cannot be equal to 1. Because if it's going to be 1, b to the x is just is 1. Okay, so b must be positive and b cannot be equal to 1. So suppose b is a positive number with b not equal to 1. If this is going to be the case, then we can define, okay, then an exponential function, an exponential function with base or at base, with base b. Okay, base b is going to be defined, okay, it's going to be defined by, this is it, f of x equal to the b to the x, or y equal to b to the x. For what x? Everything you like. For all real, of course. Values of x. Real values of x, you see, I use anything you think about it. You cannot use complex numbers. That's that's going to be the idea. So the exponential function is going to be a base, a number. That number must be positive to the x. If you pick the base to be negative, then you have to use the complex numbers. That's why we don't use it. Okay, so that would be our exponential function that we're going to have. So for example, 2 to the x, you see, for example, f of x equal to 2 to the x is an exponential function and exponential exponential function. Okay, any question? So it's going to be a machine for us, okay, a new machine. So how we're going to operate with this machine? First, we are going to graph this machine. That give us a better understanding of the nature of the function, and we take it from there. Okay, any question? So make sure you understand why the base must be a positive number. Okay, why the base cannot be equal to 1? Because if it's going to be equal to 1, it's going to be just constant. Okay, 1 to any power is 1. And we can say for a real number x, and this is it. If somebody say, oh, but how about f of radical 2, radical 3? You say, oh, I can do it, but I should use my calculator. Okay, now to get this function, we are going to check the graph of two function, then we give you all the information that we need. So this is it. We usually give you one of them on the test, okay, or on the common quiz. We want to sketch the graph, of each function. Okay, and the first one is going to be y equal to 2 to the x, 2 to the x, 3 to the x. All of them are going to be almost like each other. Okay, and you are going to see in a minute that why this is going to be the case. Okay, so as usual, we need a couple of numbers to graph it. So this is going to be x, and this is going to be y equal to the 2 to the x. Okay, just pick some numbers. If you pick x equal to the 0, for example, this is going to be 2 to the 0, which is equal to 1. Okay, if you picked 1, so it's going to be just 2. Okay, if you pick 2, it's going to be 2 squared, which is 4. And you pick a negative 1, so that gives you 2 to the negative 1. We already talked about it, 1 half. And you pick a negative 2, so that gives you 2 to the negative 2, which is 1 over 2 squared, and this is equal to a quarter. Any question? So put these on the xy coordinate, connect them together to give you a nice graph. So this is it. So x equal to 0, y would be 1. So this is going to be the case. 1, 2, 1, 2. Another point. Okay, that's a 0. That's 1. Then 2, 4, 2, 4, 2, 3, 4. So that gives you the next point. And that's a 2. And negative 1 and 1 half, it's a negative 1. 1 half, so that was 1. This is going to be 1 half. Okay, then the negative 2 a quarter, negative 2. A quarter would be just half of this. Okay, that's it. So if you graph them together or connect them together, this is going to be the case. Okay, so this function is going to be a kind of, we call it increasing function. Okay, that is going to be the one. So if we go from left to right, the function getting up, 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 up. So we call it exponentially increasing. So exponentially increasing means quick and, okay, large and quick. That's going to be the one. Okay. So many phenomena in everyday life, growth of the population is of this format. Okay, growth of the coronavirus. That's exactly the graph that we're going to have. Okay, if you invest money in the bank, okay, your investment, you get more money over the years. So it's going to be, you know, we call it exponentially increasing function. So it's used for a special model that we call it growth model, you know, in various applications that we're going to have. Okay, so this is one case. Any question? The other thing that you can understand, you go from right to left, it's from negative infinity to positive infinity. So this is the domain of the function. And the range of the function, the value of the y, as you can see, you never come here. It's all positive. So the range is going to be positive numbers. This graph never touch the x-axis. Okay, it crosses the y-axis at 1. So 0 and 1 would be the intercepts. Okay. And for the end behavior, when x goes to negative infinity, this graph getting closer and closer to the 0. So y equal to the 0 would be its asymptote. I'm going to write down all this information, just give you an idea. Okay, that's the first model. We call it growth model. Okay, and you are going to see quite a lot of this type of okay property in future. So that's when the base is bigger than 1. We need another one. Y equal to the, let's say 3 to the negative x, which is the same as 1/3 to the x. So this is the case that the base is less than 1, or just the power over here is negative. This should give us a graph the other way around. We call it a decayed. Okay, let's collect the numbers for this one. X, Y. You can use either version to get these numbers. Okay, you start with the 0, so 3 to the 0 would be 1. If you start with the 1, so that give you 3 to the negative 1, which is a third. Okay, you start with the 2, so that give you 3 to the negative 2, which is a 9. Okay, but if you put x equal to negative 1, so that give you 3. And if you put negative 2, that give you 9. Okay, so this is going to be the nature of the graph this time. So put them together to get the graph. Okay, so again the intercept is going to be the same. Okay, that give you the same thing. If x is equal to 1, that's a 1/3. It's a 1. 1/3 is going to be, you know, close to the, this is 1/3. If we get a 2, even it's going to be worse. If you get x equal to 2, okay, x equal to 2, and that give you 1/9, which is going to be here. It's close. Okay, but if x equal to negative 1, if it's a negative 1 would be 3, so 2, 3. And if you get the negative 2 is going to be negative 9. Suppose this is negative 9. You see, if you connect them together, this time is the other way around. So it start from here. You see, this is going to be, the graph, this part. So as you can see, when you go from left to right, it's a graph going down, down, down. So that would be exponentially decreasing, if you like, graph. Okay, so this part is exponentially, okay, that's exponentially increasing, sorry, increasing. But this one is exponentially decreasing. It's like when you order a pizza, it's getting cold quickly. So the temperature going down, exponentially decreasing. Okay, and that's going to be the decayed. It's the one that we use in chemistry for those radioactive substances. So the chemical substances, they will lose their masses over the years. So that's going to be the one. But the best example is something we call it Newton cooling law. And that's when you are outside of the room. As soon as you get inside, you say, oh, it's cool. So do you mean exponentially cool? Because the difference between your body temperature and the temperature of the room is going down exponentially. So that's why quickly you feel that it's cool. So there are going to be quite a lot of phenomena, in science, depends on these two type of arguments. So we have a special model. That model is called exponentially growth and decay model, and we're going to see it in this course. We discuss it even in calculus in more details. But the growth of the population, you see the rate is 2%, 5%, then we can have a model, and then this would give us a prediction. Okay, with this model, we can predict what would happen in the next 6 months. But the decade give you the past. Okay, you know that when they discover a fossil or a dinosaur, so it's 6 million years old. The way they find out, this is going to be the nature of that reduction, decade of they call it volcanic rocks. It's kind of a potassium, and they know the nature of the potassium, and they can find out what's going to be the time. And even it's used by FBI when there is a murder. As soon as the police arrive, you see, later on they tell you that it's happened last night at 8 p.m. The reason is this one. They know the temperature of the body and the surrounding area. And then they put them together. There is a nice modeling for all of them. So they can find out from the rate that the temperature has been reduced, they can find out when it's happened. So there are quite a lot, interesting phenomena regarding these beautiful functions, exponential function. So, so what I'm going to do is you have some observation over here that we can check it. You see the domain of the function. You can go from right to left, whatever you like. So the domain would be all real numbers. The range of the function, the y, how far you can go up and down. There is no down, so no negative numbers. It's all positive. Okay, it's going to be all positive, so that's going to be the range, and some other property that I'm going to write it down for you all together. Okay, any question? So as you can see, if the base is bigger than 1, is increasing. If the base is less than 1 or this power is negative, it's going to be decreasing. Okay, so I put them together and give you some nice property, the one that we need to know, and a couple of problems that you have depends on these properties. Okay, so there you are. What is properties? Okay, properties of this function, of the function f of x equal to, let's say, b to the x, exponential function. Okay, you know that the base must be just a positive number, and we are going to use all these properties in the problem that we have. The first part, the important part, is the domain. We talk about it, x can be any number, and I'll show you how to find it. Okay, x can be positive integer, negative integer, fraction, even radical 2, radical 3. So the domain is going to be all real numbers. R is defined everywhere, but the range is positive numbers only. Positive numbers. In particular, b of x is never zero. It's always positive. Okay, and that would be very, very useful. We use it in several places. So b to the x is never zero. Okay, and b to the x is always positive. Because the base is passive. You see, if you have 2 to the x, it's never zero because of the 2. Okay, and the base, base is a passive number, so that's always positive. We are going to use it. Okay, the other property is going to be the one we talk about, the graph. Okay, so there you are. If b is bigger than 1, you know that the graph of y equal to b to the x is increasing, up, increasing. Okay, it's going to be increasing. Okay, and also b to the x. Okay, b to the x goes to positive infinity. Okay, whenever x goes to infinity, positive infinity, and it goes to 0. And b to the x goes to 0 as x goes to negative infinity. So y equal to the 0 is a horizontal asymptote. It's the observation that we have when you graph it. And this is the shape of the graph. Remember, the y-intercept is the same, and it starts from the asymptote going up. So this is going to be y equal to the b to the x when b is bigger than 1. So 2 to the x, 4 to the x, 3 to the x are all the same. These measurements would be different, but otherwise, you see, that's it. Up. Okay, any question? That's a growth function. If you change it into if b is less than 1, now it's decreasing. Okay, the graph, of y equal to the b to the x is going to be decreasing. Okay, everything else is going to be the same. So we get the 1, and it's coming down. So this is going to be y equal to the b to the x when b is less than 1. Okay, we have two models if you like, decreasing, increasing. But if it's going to be on the test, you have to give us a couple of numbers, okay? Because we know that this is going to be the graph in general. But you have to give us a couple of numbers to show that you did graph it, rather than just give us roughly, okay, what the graph looks like. So this is going to be another property that we're going to have. Now algebra, it's just property of the exponents that we have. In algebra, we just remind you that b to the 0, of course, is 1. You know it. Okay. If you have a b to the x1 times b to the x2, okay, that's a b. So you know that in this case, it's going to be b to the x1 plus x2. If you multiply with the common base, you add the exponents. But if you divide b to the x1 divided by b to the x2, you know that we subtract the exponent. Subtract the exponent. If you multiply, we add. If you divide, we subtract, and we need another one. If you have b to the x1 already, but you want to raise it to the new power, so this would be b to the x1 times x2. We call it the multiple powers if you have an old power and the new one. So we just multiply them together to get these properties. Okay. And the last but the very important part is we talk about the one-to-one, we talk about the inverse function the other night, and this is that property. That property, we call it one-to-one. One-to-one property. What is one-to-one property? It is that if b to the x1 is equal to the b to the x2, remember the bases are the same, so the only possibility is that this top value must be the same. And that was exactly one-to-one. That was the one that we talked about, remember? Every horizontal line would intersect the graph of the function at one point only. That is the geometry of this, this. I can write down for you. So this means geometrically, if you like, this means every or each horizontal line, horizontal line intersects the graph of y equal to the b to the x at no more than no more than 1 point. Okay, 1 point. That's exactly the same thing that we call it, one-to-one property. You know that this is it. This is the graph. And if you take any vertical aspect, any horizontal line, that would intersect the graph at 1 point only. That's why if the bx1 equal to the bx2, then you must conclude that the x1 and the x2 are going to be the same thing. We use this, especially last one, to solve some equation. And this is your first problems. You have a group of them in your book, and that's why we want to take it away. Get to this point so that we can give you those, those examples. Okay, so any question? So let's get down to these uh, examples that we're going to have. And this is your first sets of problems. Example. Okay, and that's it. We want to solve each equation. Solve each equation. You probably have seen this type of equations, but we are going to give you a couple of parts when we get to next quiz. Okay, are you ready? The first one. We are going to use just this property of the exponents that we talk about it only. Okay, so this is it. It's going to be 5 to the 5 to the 3x plus 1, which is equal to the 625. Remember, there are some other methods to do it, but now we can use, let me just explain it for you. Solve each equation using only one-to-one property. One-to-one property, okay? In future, we have another method, but this is the one that you have to check first. You see, look at the base. The base is 5. You have to try to write 625 in terms of the 5, okay? Any suggestion? 625 is 5 to the which power? 5 to the 625. 5 squared would be 25. Okay, 5 to the third would be 25 times 5 is 125. 5 to the fourth is 625. Okay, 5 times 5 times 5 times 5. So this is how we're going to check these type of problems. Solution. Okay, 5 to the 3x plus 1 is equal to the 5 to the 4th, you see? Now we can use one-to-one property. 5, 5, so the top must be the same, okay? So you have to get to this type of form, if you like. So as soon as we get this one, we say, so by one-to-one property, this is it, one-to-one. So that give it 3x plus 1 must be equal to 4. So for x. So that give it 3x equal to 3, and the x is equal to 1, and you're done. Okay, any question? So we have to try to change it into this format to be able to do it. That's a kind of type 1. Ready for the second one? The second type. That is the second type is 16 to the 2x plus 1 is equal to the 32 to the x plus 1. Again, you have to check, to think about it. You have to have the same base. So try to write the 16 and the 32 in terms of the exponential form. It's clear 16 is 2 to the 4th, and the 32 is 2 to the 5th. So let's try. It's 2 to the 4th, but you already got the power raised to 2x plus 1 equal to 32 is 2 to the 5th, 2 to the 5th, but you already got another power, x plus 1. Okay, so now what we have a kind of old power, okay? We have the old power and the new power. You see, old power and the new power. So what we're going to do is we are going to multiply them together. So that give you 2 to the 4 times, 4 times 2x plus 1, which is equal to 2 to the 5 times x plus 1, 5 times x plus 1. Okay, 4 times 2x plus 1, 5 times x plus 1. Now we have the same base here. You see, we have the same base, so we can use the one-to-one property. Okay, so this is going to be one-to-one property. So the top would be 4 times 2x plus 1 equal to the 5 times x plus 1. Okay, now you know how to solve this equation. You distribute it. It's going to be 8x plus 4, and this is going to be 5x plus 5. And we solve for x. Okay, so it's going to be what? 8x minus 5x, and that give you 5 minus 4. So that give us a 3x equal to 1, and then x would be 1/3. You see? So that give you the final answer. Any question? Just refreshing your memory regarding various type of the property that we have to use. So old and the new one, so just multiply them together and you get these numbers. So the idea is you have to get the, you get the same base. Okay, any question? And
Yeah, quick question.
yes.
What if we were to broken that down to 4, like 4 squared and then
No, it's not going to be good. Because what do you do with the 32 then?
4 cubed?
No. Now 4 cubed would be 64.
Oh, yeah, you're right, my bad.
Yeah, you can't do that. You have to go with the 2 because, you should be able to get to the same, to same base. That's what. Okay. So there is one more, and you have it, in your assignment. Let's see what is the other one. Is going to be, number 3. What is the third one? The function is of this format. You see, it's going to be 3 to the, we have the 3 to the x squared minus 3x. X squared minus 3x, and this is going to be equal to the, it's equal to 1/9. That is going to be the case. Okay, any suggestion for this one? The base is 3 here. Okay. Yeah, that's going to be 9, so it's going to be 3 squared. Yes. So let's see. So the solution is going to be, so that's going to be 3 to the, it's going to be 3 to the x squared minus 3x. And this is going to be what? It's going to be 1 over, 3 squared. Okay. Now we can move the 3 squared up. You see? Because there is no other chance. So we write it down as 3 to the negative 2. Okay, any question? I just wanted to know that these, how can it's going to be possible? We are going to do the same thing when we get to the log function. That's why we spend a little bit more time to do the algebra so that in future we be fine. Okay, now we get the same base. So the top must be the same. X squared minus 3x is equal to the negative 2. Now you have to solve this equation. You know that you move the 2 to the other side, it's the quadratic. So that would be 2 equal to the 0. And you may have to use factoring or quadratic formula. In case it's nice, you can factor it. Okay, so that will give us what? It would give us x minus 2 times x minus 1 equal to the 0. So we have two solutions. X equal to 2, one solution. Okay, and the x equal to the 1 is going to be another solution to get these numbers. Okay, so these are various possibilities that you may have to impose, and we give you a couple of them as one question when we get to the this coming quiz. So make sure that you are ready for it to get these numbers. Okay, any question? So that give an idea of the machine that we are going to have. We call it this exponential function. But when you are going to be in application, you see the case that we use, we just give you a b. B was a base, if you like, and okay, b can be any positive number. So somebody can have 2 to the x, 3 to the x, 5 to the x, 7 to the x, etc. But the way we are going to use this type of function in science, it doesn't matter. Business, okay, biology, physics, electrical engineering, there is a one base that's very consistent with all these type of phenomena that we're going to use. That base is very popular, okay, and that base
Small big hat.
would form a special function that we
B,
call it
that means
natural exponential function. That base is e, yes. Okay, so let's give you finish it with this definition, but we leave it for the next class. Okay, so the one that we are interested in is this function. You're going to use this one only when we get to the calculus or the application problems that we're going to have. So what is natural exponential function? Okay, exponential natural exponential function. Okay, in your book, they give you two different sections to introduce this one, but I wanted to give you an introduction. Then we start working on this one when we get to the next level. Now, what is going to be this base? A special base. So what is that base? So this function, it's defined. Okay, it's defined by this function, by y equal to e to the x. Okay, what's e? E is like, pi is irrational number, remember? It's a 3.14, it's not 3.14, it's going to be just estimate of 3.14. E is a similar number, if you like. E to the x is irrational number, and this number is like, is approximately, it's like 2.7, okay, 2.71828, it's go on forever. Okay, is an irrational number. You cannot write down as a fraction. These never end. Okay, is an irrational number. Irrational number. Some people they call it, or Euler, Euler Swiss mathematicians say they call it Euler's constant. And wrongly they say that it's Euler constant because it's the start with the E. Nothing to do with that. Okay, that E was exists, this one, even before the Euler. Okay, but Euler has done quite a lot about it, so that's why we call it Euler constant. Okay, the story of the E is very interesting. You need a little bit more information. When you are in calculus, we have different tools to introduce this one. But at this time, in the book, they have to go through some other tools. These are all the tools that we learn in calculus. But they use these tools to estimate it for you. One of them in your book is just to explain it, but you don't need to use it. So when we say e to the x, this is going to be the base. But if you want to operate with this function, all the properties that I talk about it are going to be true. But if you want to evaluate it, for example, e to the fifth, e to the 7, e to the 8, you are going to use your calculator. We use this one quite a lot. I just want to remind you, but we are going to go through it next time. You see, this is going to be your calculator. And in order to do the operation with the e, this is ln, okay? Just turn it on. Okay, this is ln that we're going to use it. We introduce this function next time. Okay, ln function, you have to go with the second, and then you click on the ln, and you will see the e. Okay, you do see this one quite a lot. So for example, if you want to find the e to the negative, 0.25, you get a 0.25 and you click, and that give you the number. Okay, even you can go with the negative numbers. You see there's going to be again the e. If you want to find something like negative 0.325, okay, so that give you the numbers. Oh, that's error. So I made a mistake somewhere. So these are going to be various, okay, various format of this function. So get to know it, because we would like to apply this one and give you a couple of application problems. Nothing difficult, but just be able to work with it. Because if you want to take any course after this course, you have to deal with this famous function. Okay, in your book, they talk about this one in two different sections, but we are going to talk about it, and get this information before getting to the next part. That would be enough. I continue this one, on Wednesday to give you a better idea. Okay, so get to know these preliminaries that I talk about it, but we are going to be investigating the E and give a couple of examples from different part of science, okay, from business, okay, biology, chemistry, just working with this function and how we're going to work with this function and using calculator, okay? And we continue. That's it for tonight. That would be enough. Okay, any question? So we continue these sections on Wednesday to see how far we can go for, prepare for the quiz. Okay, take care and have a nice one. See you on Wednesday. When I finish your grading, I let you know. Then if you have any question, email me. Just wait for me, to finish it first. Okay, that's going to be fun. So have a good one. Bye-bye.